Alrighty. Dope.
Cool. All right, Jason, you let me know. Good. Good. All right. Well, welcome back, everyone. Hope you had a good time working on the demos. Thanks for sticking around for research. We have some really solid presentations today. We want to go through a couple things before that, though. If my thing works. Yes. Of course, if you haven't signed in yet, please sign in. Please, please, please sign in. There's a lot of perks of being a member, and you have to sign in to be a member. So please sign in. If you're interested in joining any interest groups, head over to ritsec.club/about. We have a lot of interest groups, great things, a whole bunch of topics: reverse engineering interest group, penetration testing interest group, physical security interest group. If you're interested in any of those, details on the website and in Workplace. Speaking of Workplace, if you're not part of Workplace already, please join. Go to this link and create an account. That's where we hold all of our events and documents and the like. That's our main form of communication as well. So please, please, please join that. And if you're not signed up for the newsletter, if you want to see what we're doing every week, please put your email on that link right there. If you're interested in joining the hackathon, that's September 26th, 24-hour competition. We're running it in Discord, I believe. Basically, you get a project and you just work on it for 24 hours. A lot of fun. I've heard great things about it. If you're interested in that, more details on Workplace as well. And of course, if you're interested in presenting your research, I have a couple different things for you. Probably heard this spiel before, but the sign-up link is presentations.ritsec.club. If you don't know what to present on, ideas.ritsec.club. It's a public document. If you have an idea but don't want to present on it, you can throw it down on the list there, or you can take an idea from the list, either one. Also, we have co-presentations, which we have 2 of today. I'm glad to announce that. If you're feeling a little iffy about presenting on your own, don't feel like you know enough, ask someone to present with you. Some people put their names next to ideas on the list. Reach out to someone from eBoard or someone from previous eBoard or anyone who's a prominent member of the club. It's a really good experience. Presenting is great. And of course, for presenting, we also give you free stuff. So there's a document in Workplace. It's called Research Swag. I'll try and post it again soon. It's somewhere on my profile. But we give you free stuff for presenting. We just want to extend a thank you for taking the time to do research and present it to the club. So of course, there's like lanyards, water bottles, lockpick set, and further on, there's more and more cool stuff. So go check that out. And Emmanuel will take this slide.
Yep, just like before, I'm looking for a junior tech lead. So if you're really interested in creating challenges, you can apply at that link. You don't have to know a lot of things. It's just about you learning and the ability to just keep pushing. That's all I want. And yeah, so apply and we'll see. Let's go.
Thanks, Emmanuel.
Okay.
And Philip's going to take this slide as well.
It's the time of the year for CCDC. Like I discussed before, it's a really good learning opportunity. We're going to try and start meeting next Friday, 5 to 9. We don't really have a location right now. We're going to figure that one out. And then we'll also be in Discord in case some people who can't get in person can be remote. But again, CCDC, amazing opportunity. Learn a lot of stuff. Just come, even if you don't know much, even if it's kind of intimidating, if you come, we will teach you and it'll be great. As long as you have the motivation or the attitude to come, you'll be just fine. It's a big commitment, but it's gonna be a fun time. Every Friday, 5 to 9, probably start next Friday.
Awesome. John?
It's almost time for Career Fair, and we host Career Fair Eve, where we get to meet with sponsors. There's not an official date yet because I have not decided based off the nice long 2-week career fair that is happening at the school. But I want to let everyone know to start getting your resumes built up. We're going to have a resume night soon. It is going to be great. Start working on your resume if you haven't already. Even if you're a freshman, you should still make a resume. So please, 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 please make a resume. And please, like Enzo said, sign in so you can be a member, because this is for members to talk to the sponsors. So please, please, please sign in. Awesome. Thank you.
All right, and the last thing I think for events is, of course, Hack Night. These are Tuesdays, 7 to 9 p.m. It's a great time. We chill in Discord. We chill in the labs as well. I think we were in SysLab last Tuesday, and we got to meet a couple of you guys in person, which was really cool. So if you guys want to stop by and meet some e-board members, we'll help you with your homework, or if you just want to work on something, help with the challenges, anything like that. It's a fun time. Keep an eye out on Workplace for more socials. And of course, round of applause for our sponsors. We couldn't do it without them. So thank you to all of our sponsors. We really appreciate you. And lastly, make sure to follow us on social media, Instagram, Facebook, and Twitter. And the disclaimer, of course, everything you learn here is for educational purposes only. Please don't do anything malicious with the information that you learn here. So the news for this week. So the first thing that I found this week was this attack called Meowbot, which I thought was kind of funny. Basically what it is it's a large scale attack that scans the entire internet for insecure databases. So say someone just configures some sort of a database on AWS or something like that, but they don't secure it yet. Like they just release it and it's publicly available to the internet. This bot, basically what it does is it's just scanning the internet for that sort of thing. It's somewhat malicious. I mean, once it finds an instance, it overwrites all of the data in the database with Meow, which is an interesting thing. The question is, why are unsecured databases such a popular target? And this is somewhat obvious. Sensitive data is often kept within databases, so obviously that's a shining beacon for attackers. And also, it's very easy for these databases, these unsecured databases, to be found. It doesn't take a massive supercomputer to scour the internet for cloud instances. Doesn't take that long. Sometimes it could just take a couple of minutes with a normal computer. So that's also why it's such a popular target. So how are these being prevented? So a good practice of what services are doing now is having security features pre-installed that prevent these sort of things from occurring in the first place, and making it so it's very difficult to turn off these features. And also having your own external scanning system yourself, having a program in place that does this exact thing is a good way to make sure you're covering all your bases and making sure nothing's left unexposed to the internet. This one was also pretty interesting. So by 2024, this is kind of an interesting statistic. 75% of the top level people of companies are going to be responsible for CSP related incidents, which CSP is, I think it's like cybersecurity dash physical. So anything that involves an incident where something is breached or hacked and it involves something physically that could hurt someone or be a fatality or something like that. The top of the companies are now being held accountable for this stuff. So what does this mean? I just kind of explained it, but since everything is so integrated nowadays, we rely on these IT systems. These breaches can no longer be tolerated. So every time an event happens, more rules and more regulations are going to be put in place. It's going to be harder for them to kind of shift the blame down lower. So this is good for us, I suppose. Obviously, with this, with them wanting to cover themselves, It'll put a much stronger focus on cybersecurity and securing your systems, which is good for us. There's a little money statistic down here. It was about 250 million spent in 2018, and by the end of this year, it's estimated to reach $1.15 billion. So pretty cool. And lastly, this thing today, I don't know if you can read this, trusted tool. So I don't know if you guys know what Docker and Kubernetes is. Basically, it's like you run services on like low weight machines, or it's not quite a VM sort of thing. It's a small lightweight thing where you can run a server or something like that. Basically, there's this trusted tool called WeaveScope. Basically, there's this long description here. TLDR, basically, it just shows you a complete view of your infrastructure and allows you to fix any issues that WeaveScope, I guess, finds through the app. So it's basically an all-in-one tool to monitor all your instances. So for malicious parties, instead of deploying malware, they use this tool to give full visibility and full access to all of the assets. So for an example walkthrough, they find a misconfigured, port. This is like the most common way to, infiltrate these sort of things, misconfigurations, that sort of thing, to create a privileged container. And then they have that container be mounted in the file system. So now all of the files are now accessible to the malicious party. And then, of course, instead of installing malware, they install this respected tool by actual security researchers on the victim, and they connect it. It default connects to port 4040. And now the attackers have full visibility and control of the entire infrastructure. This is mainly a result of cybercrime group Team TNT. They've been using it a ton recently. Basically, this is just a giant backdoor, I suppose, using this tool, which is pretty cool. I think that's all I had for the news today. So I will turn it over to Newman once again. He presented last week, and how he has another awesome presentation for us.
All right, let me just share my slides. Cool. You got the slides sharing, maybe? Cool, I see it up on Twitch. All right, let's get started. So, folks, today I'm going to be talking about CBC padding oracle attacks. This is a cryptography attack that allows you to decrypt a plain text without using the key 1 byte at a time. So to decrypt a single plain text, you would maybe do at most a couple hundred attempts per byte. So depending on the length of your plain text, that could be a few hundred to a few thousand attempts to decrypt, which sounds like a lot. But when you compare it to the incomprehensibly large number of attempts you'd have to do to just brute force the key, it's a far more efficient attack. First, let's do a quick overview of the agenda for today. We'll start off with a quick review of block cryptography. If you've done some cryptography before, if you've taken a class, this will help refresh your memory and bring that back up so you can remember what CBC and block cryptography is. If you haven't done cryptography before, after the review, you won't pass any tests, but hopefully it'll give you enough information so you can follow along for the rest of the with the rest of the talk. And if you end up feeling lost anyway, don't worry about it. Just eventually, in the CSEC program, I know we have a cryptography class. Come back and watch the recording after that, and hopefully it'll make sense. But with luck, if I do a good enough review, hopefully everybody will be able to follow along. So after we do the review, we'll talk a little bit about what padding oracles are, and figure out what kind of behavior we can expect from them. After that, we'll talk about how we can actually attack a padding oracle to decrypt a ciphertext without the key. After we do that, we'll talk about a couple real-world implications, reasons that this is possible, and how you could prevent this attack if you were running a server somewhere. And then if we're lucky, we'll do a demo at the end. Before we get started, I just want to shill a little bit here. The way I found out about this attack was during my independent study last spring. I ran through and solved a bunch of the CryptoPals challenges in Rust, which taught me a ton about cryptography and crypto attacks. And if you aren't familiar, the CryptoPals challenges are a series of programming challenges designed to teach you about some cryptography and get you understanding how cryptography is implemented in the real world. And they also walk you through some real world cryptography attacks that are like actually published and presented at conferences. And these are things that would be legitimate, like actually serious findings in like a pen test report. So it's a really cool set of challenges. They start getting pretty hard, but if you want to get more into crypto or even learn a new programming language, this is a great way to do that. And I will post a link after the talk in the workplace for the challenges. Highly recommend you check it out if you're even slightly interested in cryptography. All right, now let's get into it. Quick overview on a couple block cryptography terms. So in general with cryptography, you take a plain text, encrypt it with some kind of cipher, and then you get your ciphertext. And there's a few different kinds of ciphers. There's a block cipher, which is a cipher that encrypts things, like encrypts your plain text in one block chunks. And a block is just a fixed length of data. The size of a block varies from cipher to cipher. For example, for AES, the block size is 16 bytes. And in the rest of this talk, we're only going to be working with AES. So I'm just going to assume that a block is 16 bytes long. However, it can vary from one cipher to another. Just know that. So with AES, to encrypt it, you give it 16 bytes of plain text. That's 128 bits. You give it 16 bytes of plain text and encrypts that all at once, and you get 16 bytes of ciphertext. This is in contrast to stream ciphers that encrypt and decrypt 1 bit at a time. So that's a block cipher. Block cipher modes are these kind of higher level algorithms, you could say, that use a block cipher as, say, the core building block, core building block to an algorithm that's used to encrypt and decrypt data of arbitrary length. So if you just have a block cipher, you can only encrypt 1 block of data. But with a block cipher mode, that gives you the freedom to encrypt and decrypt however much or however little data you want to. There's a number of these. A really simple one is ECB mode. And if you've ever looked into block cipher modes, you've probably seen this picture. This is a fairly textbook picture for ECB mode. Over here, we have the plain text, which is Tux, the unofficial Linux mascot. I'm pretty sure he's unofficial. This would be the plain text. And if you ran this beautiful Tux image through an ECB mode encryption, the picture would look something like this. You can kind of tell where the different colors are, and you can still kind of make out that Tux is there. So it's not great. You can tell patterns about the plain text in the ciphertext. If you used a different mode of encryption, the image would look something like this. It would be essentially random. You can't distinguish any information about this plain text from this ciphertext. You have no idea what's going on here. This is ECB mode. It stands for electronic codebook mode. In practice, it's never used. If you saw ECB mode being used, it would probably be a finding on a pen test report, because there are ways that you can recover a key or decrypt a plain text, or excuse me, decrypt a ciphertext that was encrypted using ECB mode. So this is bad. It's pretty much good just for an example of block cipher modes, but never use ECB mode, ever. What we're going to be talking about today is CBC mode. And we're going to go through, I'm going to walk you through how CBC mode encrypts and then how it decrypts. And then that'll be our cryptography review for today. So with CBC mode, you have a plain text that's however long. And the first thing it does is it'll split that plain text into blocks. And like I said, we're working with AES here, so a block is 16 bytes long. So in this diagram, taken helpfully from NIST Special Publication 838A, NIST has got some solid documents. They're pretty wordy, but if you're looking for a good reference and you're willing to slog through it, they're pretty good documents. So what we've got here is our plain text split up into a number of blocks. And each block is going to be 16 bytes long. And so to encrypt a single block, we're not going to just take this plain text block and input it directly into the cipher. No, what we're going to do first is XOR it with another block. And for the first plain text, what we're going to use is what's called the initialization vector, also known as the IV. And I'm going to refer to it as the IV just because that's shorter. So the IV is just one block that's randomly, oh, whoops, spoilers. Okay, sorry about that. The IV is just one block that is randomly generated and used for encryption and decryption. The IV can be, it should be randomly generated and it should be different for each plain text that you encrypt. But it doesn't have to be kept secret. It's not a part of the key. It's just a value that you need. It's a parameter. So for the first block, we're going to XOR the plain text with the IV. And then whatever the output of that XOR operation is going to be what we input to the ciphertext. So we're going to encrypt that block with the cipher. And that encrypted block is going to be our output. That's going to be our ciphertext. So in review, you take a plain text block, XOR it with your IV, encrypt it with the cipher, and take that output as your ciphertext. And that's how it works for the first block. For every other block, as you can see here in the diagram, we're not going to XOR those with the IV. Instead, for example, for the second block of plain text, it's going to get XORed with the ciphertext of the first block. So basically what happens is for every other block besides the first block of plain text, it gets XORed with the ciphertext block from the previous block. So for plain text 2, it'll get XORed with ciphertext 1. Plain text 3 would get XORed with ciphertext 2, and so on all the way down. And that's where the CBC and CBC mode comes in. CBC stands for cipher block chaining. So here we have our ciphertext or cipher block, and it gets chained into the next block of encryption that we're doing. So we're chaining it into this operation by XORing it with the plain text. So that's how encryption works. Decryption with CBC mode is basically the exact opposite. You take your ciphertext, split up into a number of blocks, and then your ciphertext gets decrypted by the cipher. And then whatever the output of that decryption operation is XORed with your IV in the case of the first block or the previous ciphertext block. So for the first block, we're going to take the ciphertext, decrypt it, XOR it with the IV, and now we have our plain text. For the second ciphertext, it's going to get decrypted, XORed with the previous ciphertext, and then now we have our plain text, and so on and so on. If I click between these two, you can see that they're pretty much just the opposite of each other. And this works great if you have a plain text that's a multiple of the block length. So if we had 64 bytes that we wanted to encrypt, great. 64 divided by 16 is 4. That's 4 blocks evenly divided. We don't have any remainders or decimals or anything. It's a whole number. But what if we had 65 or 66 bytes? That's an extra 1 or 2 bytes at the end there. If we had a couple of bytes at the end here that we needed to encrypt, what do we do? Well, you have a couple options. You could just take those extra bytes and drop them, like cut them off the end and forget about them. And that's not great. You don't really want to just get rid of plain text. That could either make the output look garbled, or it could totally corrupt whatever your plain text is. But the other option is just to, if you have a couple of bytes there, you could add in some random data on the end so that your plain text is once again a multiple of the block length. And that's what we actually end up doing. It's called padding. And there's a number of schemes of doing padding, but what we're going to talk about is PKCS7, which is a padding scheme that's used in some block ciphers. There's different schemes that are appropriate for different applications, but PKCS7 is appropriate for block ciphers. So we're going to walk through a couple examples of how this padding works. This is just a screenshot of an IPython terminal. So if you're familiar with Python, that's what the code we're looking at here is. So here's our plain text that we have. It's going to be 6 bytes long, and each byte is going to be a capital A. So I guess the plain text is screaming. I don't know. And since we're using AES, the block size is 16 bytes. So as you can see, our plain text is 6 bytes long. The block size is 16 bytes. Oh no, what do we do? We're 10 bytes short of what the plain text length needs to be. So we're just going to add some padding to this to make it 16 bytes long. And the way we do this with PKCS7 is we figure out how many bytes we need to add so that the plain text is a multiple of the block size. So in this case, that's 10 bytes. So we know we need to add 10 bytes of padding. Well, we have to decide what is going to be the value of each one of those bytes of padding. Are we just going to add garbage data? No, we're going to have a specific scheme. So with PKCS7, the value of each byte of padding is the amount of padding that's being added. So in this case, we need 10 bytes of padding. So we're going to add 10 bytes of padding, and each byte is going to have a decimal value of 10. So what we're doing here, this is just some Python. This is a Python construction to create an array of length 10, and each element in the array is going to be the number 10. So a length 10 array, each element's 10, and then we're going to convert that to a byte array and append that to a plain text. And now we can see our new plain text. We still have the 6 A's, the screaming, but now we also have these 10 bytes of padding. And Python's representing this. It's attempting to show it as a new line character, so \n. If you looked up in an ASCII table or, hey, a Unicode code point, you would see that for the \n character, I think it's line feed. Yeah. The line feed character has a decimal representation of 10. So we have 10 bytes here. The decimal value of each byte is 10. Awesome. And now our plain text is a length 16. So we want to encrypt our screaming plain text. So we add padding onto it, and then we can encrypt this, send it off to whoever our recipient is. They can decrypt it. They'll see this plain text with padding on it. And then to get the plain text, because you don't want to leave the padding on there before displaying it to the user, they're going to strip off the padding. And the way that you do that with PKCS7, you can use the fact that the decimal value of each byte of padding is equal to the length of padding. So all you got to do is look at the very last byte. We see that it has a decimal value of 10. So that tells us, all right, there's 10 bytes of padding. So we look back 10 bytes and make sure that each one of these bytes has a value of 10. Because if they all have a value of 10, that means that's valid padding. If one of these in the middle had a decimal value of, say, 9 or 8 or 127 or something like that, that would not be valid padding. There's no way in PKCS7 padding for that sort of thing to happen. So that would be invalid, and we'd have to handle that somehow. And that somehow is going to be very important in a moment. But I just wanted to cover one other case with padding before we talk about that. When your plain text is already equal to the block size or a multiple. So here we have a plain text. It's going to be 16 A's, even more screaming. I guess they're more scared at this point. I don't know. So we have a plain text that's 16 A's. That's a multiple of the block size. Block size 16, plain text is 16 bytes long. Great. So we don't need to add any padding, right? Well, wrong. This is a special case for PKCS7. What you're going to do is add padding, one entire block of padding. Because with PKCS7, you want there to always be padding. If there's not padding, you're going to look at the last byte of the plain text. It's going to be some invalid padding value, and that it's going to be bad. So we always add padding. And if it's already a multiple of the block size, we're going to add an entire block of padding. So here we're creating a list. It's 16 elements long. Each element's the number 16, converting it to bytes, appending it to the plain text, same as before. So we can see our screaming, the 16 A's, and then there's 16 bytes of padding. And each byte is going to be, so Python's representing this in hexadecimal. So hex 10 is equal to decimal 16. So we can see we have 16 bytes. If you counted it out, that would be 16. That's 16 bytes, and the decimal value of each byte is 16. And our plain text is 32 bytes long. That's a multiple of 16. Great. Awesome. We're good to go. That's padding for block ciphers in a nutshell. So now let's finally get into padding oracles. We're going to take a quick break for water. If anybody has any questions, post them in Discord, Twitch chat, take a look. Let your brain absorb the crypto. Think about it for a bit. All right, no questions. Let's get back into it. So CBC padding oracles, or padding oracles in general, is any kind of software or server or construct that tells you whether or not a plain text has valid padding. So in practice, how this typically looks is you'll request a ciphertext from the oracle. And the oracle will have some secret plain text and some secret key that it keeps secret to itself. You have no way of accessing, you have no way of seeing what the plain text is. You have no way of seeing what the key is. So the oracle is just quietly to itself going to encrypt its secret plain text with its secret key, and then give you the ciphertext. And in the case of CBC, it'll also give you the initialization vector. So you can request the ciphertext, and that'll be a ciphertext of some plain text that you don't know, encrypted with a key that you don't know. Then later on, you can give that ciphertext and IV back to the padding oracle and say, hey, does this have valid padding? And the oracle will tell you, yes, it does, or it'll tell you, no, it doesn't. And the way it does that is it'll use its secret key to decrypt the ciphertext you gave it, and then look at the plain text that results. And it'll try to strip off the padding. And if it has valid padding, it'll be able to do that. And it'll tell you, yay, we have valid padding. If it doesn't have valid padding, it'll tell you, nope, did not have valid padding. This seems like a pretty arbitrary construct. Like, who would be running a padding oracle? In practice, this ends up happening in things like TLS, or maybe if you're doing some really funky things in your web server with like authorization tokens. It's never intentional. It's never intentional to present a padding oracle. What often ends up happening is that there's some kind of mishandled exception. So somewhere in your decryption code, you say, all right, we decrypt the ciphertext, now strip off the padding from the plain text. And that code is going to say, oh, hey, wait, there's no valid padding on this plain text. I don't know what to do. And it'll throw up an exception exception that'll probably bubble up to the top, and you'll get an error message, like a 500 error or something like that. So it's not intentional, it just ends up happening. Quick warning, there's a light theme incoming. I wasn't able really to make this work with the new slides, so just shield your eyes if you're in a dark room. Ah, okay, super bright. So now we're going to talk about actually attacking CBC padding oracles. And I'm going to focus on, for this, we're going back to this decryption diagram that we had earlier. I'm going to focus on the second blocks, the second block of ciphertext. We're going to decrypt that right here. So let's look at the various inputs and components to this operation. So we take our ciphertext, we input it to the cipher, which decrypts it, and then we get this output block. And this output block isn't the plain text yet. It's kind of an intermediate between the ciphertext and the plain text. And we don't usually see this, but I'm going to call this the intermediate state because this is a pretty important value. Then you take this intermediate state and you XOR it with the previous block. In the case of the first block of ciphertext, you're going to XOR it with the initialization vector. In the case of every other block, you're going to XOR it with the previous ciphertext. For the sake of simplicity, I'm going to call whatever this input to the XOR operation is with the intermediate state, I'm going to call that the XOR block. So going forward, we got the intermediate state and the XOR block. So this can kind of be, this whole operation here can kind of be generalized by this equation right here. So if you have a plain text, for every byte in that plain text, so for every byte in that plain text, it is equal to the XOR operation between the associated byte in the XOR block and the associated byte in the intermediate state block. So for the first byte in the plain text, that's going to be equal to what happens when you XOR the first byte in the XOR block and the first byte in the intermediate state block. Whew, I need some more water. So just take a look at this. Think about it, meditate. Lots of XORing going on. So something that's very important that makes this attack possible is that this ciphertext, we can modify it. And with just default CBC, the padding oracle has no way of knowing that we modified the ciphertext. Now in practice, if you modify the ciphertext and you give it some other weird value, this plain text is going to be totally garbled in all likelihood. So if you're a human and you look at this and you're expecting like plain text or something, you're going to know. But there's not really a way for a computer to know that this ciphertext was modified. So what we can do is modify this ciphertext so that, and then that modification will propagate to this plain text block. So I'm just going to move to the next slide here. We have this equation right here that I have to represent it. So XOR prime with this little tick, I'm going to call that the modified XOR block. That's what we're changing. So if we modify the XOR block, we're not going to change the input block. We're just going to leave that the same. We're going to change the XOR block, and since the input block is left the same, the intermediate state is going to be the same too. And if you XOR these values together, you're going to get a modified plain text. So how can we use this? How do we know if we modify the XOR, we're going to have a modified plain text block? Well, the one way that you can do this is you can split this up. You can split up your ciphertext one block at a time. I said for a padding oracle, you have to give it one block, or you have to give it the ciphertext in the IV back. I never said how much. So what we could do is just give, for a single byte of the ciphertext, we could just give the padding oracle one byte of cipher, or one block of ciphertext as the input block, and The XOR block is the IV. So we could repeat that. The input block, we could give it that as the ciphertext, and the XOR block is the IV. And since the IV is used as the XOR block for the first block of ciphertext, that works for us. We're just not going to decrypt this. For example, for the second block, we're not going to decrypt this ciphertext. We're just going to use it as an IV when we're giving this to the padding oracle. So when we do that, we have this. Usually this is the last plain text. This is going to be what has the valid padding. But if we're just grabbing a block in the middle somewhere, it's in all likelihood not going to have valid padding. So we don't know what this last value is, what this last byte of the plain text is, but we're pretty sure it's going to be invalid. So when we give the padding oracle the input block as the ciphertext and the XOR block as the initialization vector, padding oracle is going to tell us, hey, that's invalid padding, whether that's through an error message or a 500 error or something. Maybe there's like some timing change. We're going to know that this is invalid padding. And what we want is it to be valid padding, because if it's valid padding, we know what that byte of plain text is. We know it has to be 0, 1, or the decimal value 1, because if it's just 1 byte of padding, then that value of padding, like the value of that byte of padding, has to be 1. Now, the way that we can do this is by modifying the XOR block. So if we want to make this plaintext be this byte, what we can do is just try every possible value for this byte in the XOR block. So if we're working with the last byte in the plaintext, we'll work with the last byte in the XOR block. We're going to try all values 0 to 255. And for almost all of them, in fact, all of them except 1, this last byte, it's going to be some garbage. Whatever it is, it's not going to be valid padding. But for one value of that last byte in the XOR block, it's going to produce valid padding. So then when the padding oracle tells us, hey, it's valid padding, we know that this modified plaintext is 1. So we know what the value is for this variable in the equation, and we know what the value is for this variable in the equation, because that's what we provided. We gave it this value. We know it. So what we can do is just kind of do some algebra magic and rearrange the terms, plug in what we know, and now we know that byte of the intermediate state. If we go back here, write this value. We know 1 byte of the intermediate state. And I hear you say, well, Newman, how is that helpful? We can use that intermediate state, because it doesn't change, to figure out what the original plaintext byte was. So this XOR block, we know what this is, because it's either the intermediate state, or excuse me, we know what this XOR block is because it's either part of the ciphertext, which we were given, or it's part of the IV, the initialization vector, which we were also given. And we know the intermediate state byte because we calculated it over here. So we can just find the right byte in the ciphertext or the initialization vector, plug it in here, plug in the value for the intermediate state that we calculated here, and then figure out what that 1 byte of plaintext was. Boom. Now we have a single byte of plaintext. If this is kind of confusing for you, don't worry. Don't feel like you're dumb. You're not. When I first did this, it took me like hours or even days. I think it took me like 2 or 3 days to figure out how exactly this thing was working. So if you're confused, don't worry. Relax for a little bit. Come back and watch this video, the recording again some other time. It's no big deal. It's kind of a complicated thing that we've got going on here. Crypto's always hard. So that's our first byte of plaintext decrypted. Well, let's move on to the next byte, the second to last byte. So since we know what the intermediate state is for that last byte of plaintext, we can easily modify the XOR block to be whatever we want. We can modify this XOR block to be whatever we want to make a plaintext a specific value. And that's just one XOR operation. So we can force this last byte of plaintext to be 2. And then move backwards, we'll repeat this whole operation, except instead of for the last byte in the plain text, we're going to do it for the second to last byte in the plain text. We're going to try all possible values for that second to last byte of the XOR block, and then one of them will produce valid padding. And since we set up the last byte of the plain text to be 2, we need 2 bytes of padding, and the decimal value of each byte has to be 2. So when we get the valid padding message from the oracle, we know that the second to last byte has to be a decimal value of 2. We can go back here, plug everything in, figure out the normal byte of the unmodified plain text for that second to last byte, rinse and repeat for the entire block, and then just repeat that entire process for every other block in the plain text. All right, we're going to go back. We're going to stop looking at all this monospaced font, all this math, and go back to some dark theme. So real world implications. Why the heck is this possible? So this attack relies on kind of 2 things here. 1, the crypto is what's called unauthenticated, and 2, we aren't rate limited at all for our connections. So authentication, a lot of times, the first thing that comes to mind is like username, like logging in, right? You have a username and a password. Well, this unfortunately is an overloaded term. It's got multiple meanings. Authentication in cryptography means that you are able to determine whether or not, or at least in this case, it means you're able to determine whether or not your ciphertext has been modified or tampered with by anybody who doesn't have the key. So in our case, this type of encryption is unauthenticated. We don't have the key, and we can modify the ciphertext to be whatever we want, and nobody has any way of knowing until they decrypt. There's a couple ways to fix this. You can use message authentication codes, which provide kind of like, it's kind of almost like a hash that uses the secret key of the ciphertext. So you can compute, if you have the key, you can compute the message authentication code for the ciphertext and make sure that the ciphertext is valid. There's also other block cipher modes that provide built-in authentication, and you could use one of those instead of CBC mode. And in fact, you shouldn't use CBC mode. There's other issues with it. It's not a great mode, but it's used in a lot of places still. Another option is rate limiting. So if you have like a web server that's doing this for like authentication tokens and it's providing a sort of padding oracle, one way that you could kind of temporarily fix this is by just rate limiting people or implementing some kind of fail to ban system. You, in a normal environment, should not be seeing these padding exceptions, invalid padding. That might only happen if the ciphertext got corrupted in transmission. So that should be pretty rare. So you should already be pretty worried and concerned if you see an invalid plaintext show up. But to do this attack, like I said, you got to try hundreds of different values for each individual byte. So to decrypt a single plaintext that's a few hundred bytes long, that's going to be thousands upon thousands of requests really quickly. So you should be able to see it like that in your logs and your alerts. If you're seeing like thousands of padding errors showing up, that should set off some alarms, and you should be able to implement a rate limit to kind of patch up the issue. So, all right, we've been going for about 35 minutes. I hope I'm not taking up too much time, but I'm going to try to do a demo of a padding oracle attack. So here we have, how does this show up on the stream? Give me a second. There's some delay on the stream. I want to make sure that this is kind of visible. Hello? Anybody? Does this look decent? I'm going to hope this looks decent and just move on so we don't waste too much time. But so what we have here is a client and a server, and our server code is going to have a plain text in it that we don't know.
I don't mean to
Sorry,
interrupt, but the screen is still on your
Oh, I gotta change it in Zoom.
Yeah, it's a little weird.
Derp. Sorry, folks. Try this again. How's that
Yeah,
look?
perfect. Perfect.
Perfect. Awesome. Okay. All right. Moving on. Had a little oopsie with the tech. It always happens. So we've got two terminals here, and we've got a client and a server. And the server script, I'm not going to show it to you because it has the plain text in it that we want to keep secret. And when I start it, the server is going to generate some random. It's going to generate some random key at runtime. And this server is going to be our padding oracle. So I'm just going to run it. And it's a simple Flask app, as you can see. It serves a couple of endpoints to get a ciphertext and to check the padding of the ciphertext. So it's a toy example, but it works. We also have a client, and this is what's going to do the attack for us. And I implemented multi-threaded because it can take a while. So I'm going to do -t = 1 to only do one thread. And when I hit enter on this, it'll start the attack. It'll get the ciphertext from the server and then start trying to do that decryption operation that I was talking about. And you're going to see over here in the log, as soon as I hit enter, a ton of requests going by. I don't know how well it'll show up in Twitch, but here we go. And it just shoots off those requests really quick. And I'm going to stop this pretty soon, but what this client is going to do is going to, as it decrypts one block at a time, it's going to print out the plain text that it figured out. So here's the first block of the plain text. So that's great, but that's going to take a little while. So we're going to try rerunning the client with a few more threads. And now what this is going to do is each worker process is going to print out the block of plain text that it decrypts as it decrypts it. And then all the way at the end, if it decrypted everything successfully, it'll give us a little success message and print out the entire plain text. So let's hit enter in that. Give it a little bit of time. If anybody has any questions, I'm now looking at the chat. We've got about 30 seconds to a minute, depending on how much of my CPU Zoom is sucking up. I don't really know. But this is going to go, and as you can, I don't know if Twitch is really showing this, but these logs are shooting out way faster, and they're all 500 errors. Like occasionally there's a 200 response code in there. But this should, if you're having this many errors, you should be looking at your web server. So we're seeing the blocks come out. We have a question. Thank you for doing this. Will there be a video of this somewhere? This should get posted on the RITSEC YouTube page afterwards. Yeah. So we're getting the blocks. It's coming out so slowly. Zoom is really sucking up CPU, but it's coming out. We're getting the last few blocks, and boom. Common copy pasta. We've got the whole plain text here, and we've also got 5 bytes of padding. And if you remember from the PKCS talk, or the PKCS part at the beginning, each one of these has a decimal value of 5. And I didn't strip those off because I'm lazy, but if I look at the server code, just to make sure we got the right plain text, you can see this plain text constant is set to the same thing as what we decrypted. And we did it. We didn't have the key, but we were able to decrypt it. And if you want to take a look, all of this code that I have is up on my GitHub. I'll post a link to it in Workplace later on. But for now, let's go back to the slides to finish up. Oh, no, wrong slides. Those are the ones that we want. There we go. So, talked about real-world implications. We did a demo. Hopefully now you know something about CBC padding oracles. In the future, I'll talk more about like how the actual vulnerabilities that come out, like Poodle and Golden Doodle and Zombie Poodle, actual vulnerabilities that use padding oracles. But they require a little bit more knowledge about TLS. So hopefully in a future talk, I'll be able to get into how those things work. But for now, that's the end of the talk. Here's a cat picture, paying the cat tax. Thank you, everybody. I'll be in Discord and the Twitch chat if you have any questions, or always feel free to shoot me a message on Workplace. But that's all for me. Thanks. Thank you very much.
Awesome.
And I'll
Thanks, Newman.
pass it back to you, Enzo.
Awesome. Well, that will most definitely be posted afterwards. And I'm sure Newman's willing to answer questions whenever. Awesome. All right. So next up we have